Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. In this video, I'll be answering question 8 of the 2020 Board of Studies Extension 2 trial paper, and this is a continuation of a series where I'm systematically working through all of the questions on that exam. Question 8 tells us to let fx be a function over some domain capital D, and then we're asked which of the following statements could imply that the limit as x goes to 0 of fx is equal to 0. And then we're given these 4 options, and there's a lot of symbols here, and it can be quite off-putting if you're not familiar with these symbols. But as we'll see as I work through this, once you're kind of comfortable with what all these symbols mean, the question kind of reduces to what ends up being fairly simple and straightforward. So to kick things off, what I've done is I've kind of written up what we're dealing with, and in anticipation of drawing some diagrams, I've just created a few Cartesian axes here. I think often with math questions it can be helpful to visualize what you're dealing with, and I think this is definitely an example of such a question where drawing up a diagram will help. Just to kind of deal with all of the symbols that we're seeing. Basically, what you may have noticed is on all 4 options, the first part of the statement was the same. So rather than repeating it, I figured I'd just write it once. So that first part of all the options, what it tells us is we've got this upside down A, which you can kind of think of as for all. So we're basically being told for all epsilon greater than 0, so there's some value that's going to be positive, and for all possible positive values, there exists, so this backwards capital E means there exists some value, again a positive value we call delta, such that for all values of x within the domain, so included in the set of the domain capital D. So that's kind of what we're starting with. So for all positive epsilon, there exists some positive delta such that for all x in the domain, and then we have our 4 options. And often with multiple choice questions, you can kind of, I guess, get a grasp over what you're dealing with by noticing the differences between the options. So notice that in option A and B, our x value in our domain, the magnitude of it is less than this delta, and in C and D it's greater than this delta. And then in A and B, the value of the function is either less than this epsilon value or greater than, and the same with C and D, less than or greater than. So we're basically given this mutually exclusive and exhaustive set of possibilities, and so noticing that is going to help us in terms of kind of striking out options that can't be correct. Now at this point, I think it might be helpful to start drawing a diagram. And I think in terms of the diagrams, I'll give a few examples of, I guess, functions where I know that as x goes to 0, we kind of have the limit of the function going to 0. Because it's through simple examples that I think we can decipher what's going on. Now the simplest example I can think of where this is true is a function of a straight line going through the origin. So if I, maybe I'll draw it up in black. So if I just draw the simple function y, or fx is equal to x. So it's just this straight line going through the origin. Fx is equal to x. So what we can see that as the value of x goes to 0, our function also goes to 0. So the limit as x goes to 0 of fx is 0 in this case. So it's a handy example to look at. And kind of we're told that there's some epsilon that's positive. So I might just maybe in red just annotate that onto the diagram. So let's just say there's some positive value of epsilon. And there's also some positive value of delta. And maybe I'll just annotate that on here. It doesn't really matter where I put it, but as long as we know it's positive. And the reason I know to put the epsilon in this axis and the delta in this axis is because in all of our options, our epsilon is being compared to the value of the function, and our delta is being compared with the value of x. So that's kind of, if that wasn't clear, that's why I knew to do that. Now, let's kind of, maybe we'll focus on the epsilons first, because if we can work out whether we're concerned with epsilon being less than some value, or sorry, our function being less than epsilon or greater than epsilon, then we can right away strike out two options. So if we're concerned with our function coming towards 0, as x goes to 0, so if we come as x goes to 0, we want to know, does the function go towards 0? What we're really asking is the value of the function less than this value of epsilon? Because this epsilon we know is positive, so, and we know therefore 0 must be some value less than whatever epsilon happens to be. So right away we can see that if we want to imply that the limit as x goes to 0 of this function is 0, we're looking for something where the value of the function is less than this epsilon. So right away we know we're concerned with these options where we're looking at the function less than epsilon. So these ones where the option had greater than epsilon, the function greater than epsilon, we can strike those out right away. And so we've reduced this question to, again, a flip of a coin. We've got a 50-50 chance now of getting it right. So now we can think about comparing how we should compare x with this delta value. And again, if we remember that we're concerned with x going to 0, and if delta is positive, that means we're kind of going in this direction towards 0, then again, we're really concerned with thinking, well, when when x is less than this value of delta, then is the value of the function less than epsilon. If those two things are true, then we know we're heading towards 0. So we can kind of conclude that actually in choosing between, do we care about x being less than delta or greater? Well, we care about less than, so we can strike out C, and the answer is A. And I probably should have mentioned that this symbol here means implies, and that's kind of what we were told with the wording. So what we're saying is that when the magnitude of x is less than delta, if that implies that the function is less than epsilon, then we can conclude that that therefore implies that the function is going towards 0 as x goes to 0. So that is how you'd answer the question. Maybe what I'll do briefly is just show another simple example to kind of really reinforce these ideas, just in case perhaps that hasn't fully sunk in. Let's give it another crack and see with another simple example whether the idea starts to make a bit more sense. Because another example where I know that as we go towards 0, the function goes to 0. Another simple example, there's lots of examples, but one that I think of quite instinctively is x squared. So I've just charted fx equals x squared, and you can see visually that as we get closer to 0, the function kind of comes to 0, and you could, again, just annotate some value epsilon, positive value, since we're told epsilon is positive, delta is positive, positive value of delta. And again, in a very similar fashion, we know that we care whether the function is less than delta, because if it was greater, then we'd kind of be going to infinity, but we're not concerned about infinity, we're concerned about coming to 0. And again, we want the magnitude of x to be less than delta, so that the idea is if we pick a value of x that's less than delta, and that implies that the function is less than epsilon, then we know that as we come towards x equals 0, the function also comes towards 0. So hopefully you can see also with that example, exact same idea, and you get to the same conclusion. So yeah, that's how I'd answer that question. Hopefully that's all made sense. If you did find my explanation helpful, please be sure to give it a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.